Welcome to day 2 of our MLOps unit. Recall that MLOps is the standardization and streamlining of machine learning lifecycle management. In our last lecture, we went over each stage of the lifecycle, what tasks we perform at each stage, and who we collaborate with to achieve those tasks. In this lecture, we'll discuss the tools that we can use to deliver each stage of the ML lifecycle. There are some unique challenges in MLOps because deploying software code into production is fundamentally different than deploying machine learning models into production. For example, in a real world production machine learning system, data is constantly changing. We need to make sure that our models are adapting accordingly. It's not enough to just track overall performance health of our ML services, for example, measuring latency and errors. We also need to monitor for model quality, accuracy, and fairness. Specialized talent in the data science and machine learning engineering disciplines is required to properly manage these systems. Another particularly interesting challenge in ML ops is that these systems rely almost entirely on open source software. With ML systems, we have our traditional open source software security and availability issues, and we add to these the complexity of ensuring that our AI or ML models themselves are what they claim to be and have the strengths that they claim to have by being trained on the data they claim to have been trained on. It's also important to understand that different machine learning families have unique considerations. The diagram on the right shows the different families of artificial intelligence and machine learning based on how the different families operate. Statistical machine learning functions in a fundamentally different way than deep learning, which in turn functions in a fundamentally different way than reinforcement learning. Each AI or ML domain has specific infrastructure requirements and therefore implications for production. It's important to note that, despite the huge amount of attention they are currently receiving, generative language models are only one kind of AI/ML model. They fall under the umbrella of deep learning based models and are only one type of generative AI. One popular approach for making generative language models more impactful is to pull in additional context from knowledge bases, a process called retrieval augmented generation, or RAG. In order to implement RAG, we need infrastructure that a statistical ML model may not need. Requirements for our inference endpoints, the API endpoints that serve the model and provide some output on unseen data, are going to vary dramatically between statistical ML models and generative language models. In our overview of MLOps, we're going to try to keep things as high level and generalizable as possible. But keep in mind that your MLOps architecture and infrastructure will need to be specified according to the task that you're trying to achieve and the data that you're using. When learning about machine learning and AI, most of us are guided through the process of cleaning data, experimenting with different model architectures, and conducting a one time evaluation of the model's performance. We learn the tools and techniques for experimental ML, but we rarely are introduced to production ML. Let's look at the differences between these environments now. In experimental AI and ML, most of our work takes place in Jupyter notebooks. We're usually working with a small number of users, either working collaboratively in a small team or working individually. In fact, many of us will rarely even use source or version control for collaboration. It's common for data scientists to just email each other a notebook file and a requirements.txt file instead of using Git. In experimental AI and ML, our data is usually based on ad hoc queries or CSVs. We're generally working with historical and static data, and we track our data through manual processes. When cleaning our data, we often use techniques that don't translate to real world production use cases. For example, we may simply just drop missing data or outliers. In production environments, we need to make sure that we can log or provide error messages for missing data, as it's often meaningful. For example, missing data could be indicative of an issue in data ingestion in a warehouse, or that we may need to revisit contracts with calling services. When working in experimental environments, our feature engineering rarely needs to extend beyond our local testing. We persist our engineered features in memory, including scaling and encoding dictionaries. We often manually fine tune our models and record the model's performance metrics and hyperparameters in an ad hoc fashion. Likewise, our results are also tracked in an ad hoc fashion, and model binaries and results are saved to local disk. We only need to conduct inference a handful of times for our experimental results, so we never consider how we might need to scale our inferencing capabilities. Production AI/ML has dramatically different requirements than experimental AI/ML. In production ML systems, we're running distributed workflows that need access to standardized features where data and model lineage is tracked, and feedback loops and drift detection are integrated into the workflow. Production ML systems will include formalized data cataloging methods for data verifiability and lineage tracking. We automate data transformations using data pipelines. Feature engineering is persisted in feature stores, and any data scaling and encoding techniques we may want to use are persisted and reproducible. Model training practices have standardized workflows where hyperparameters are automatically logged, models are tracked in version control, and retraining is automated using scheduling techniques and deployed on appropriate endpoints with optimized compute resources. Inference is conducted by using API endpoints that can be scaled in response to demand. The model's signature is made available to other services so that they can easily interact with our data model, and we've carefully considered the requirements for batch versus online inferencing. Lastly, in production ML, our model will continually run in our environment for some duration of time. That means it will be operating on continually novel data. In order to make sure that our model is still useful and doesn't become a random number generator, we need to implement tooling that lets us detect drift and anomalies, and that we're monitoring our model's output. In brief, moving from local experimentation to a mature production environment is a complex process. However, we can break it down step by step using the ML lifecycle to make the process more manageable. There are many open source tools available that help us implement efficient, scalable, and cost effective ML and AI. Let's walk through the steps for productionizing our ML models. The first step is model development, which involves building and testing the model. In this step, we're generally using Jupyter notebooks and test datasets that may be in CSV format. The second step is when we prepare our model for production deployment. In this step, we need to refactor our training code so that it can be automated in a production environment. We may implement API endpoints for our model to interface with other production services, and we want to make sure we add in logging and observability capabilities into our code. Going from experimental to production ready code can be a challenge if you don't have design patterns to build on top of. Part of preparing for production is building data pipelines for data ingestion and processing. We don't use CSVs in production. We want to make sure our data is available in a database or warehouse. We'll build queries to pull that data into our system at training time. When we're running our models in production, we need to make sure that we've accounted for retraining. Training in production systems could be defined given a schedule. For example, retrain every week, or it could be defined in relation to some other signal that we can pass to our system. For example, if we start seeing a drift in the number of positive decisions in a classification system, we may wish to retrain. Model deployment is a step where we actually deploy our ML system into a production environment. This involves making sure that the trained model's weights are available to any system that needs to interact with it. Next comes inferencing, which is the process of making decisions about unseen data, taking actions, responding to prompts, or classifying data using the model that we've trained and deployed. Then we need to actually serve the model's outputs to our users or downstream systems. The last step is monitoring, where we continuously monitor model performance and determine when maintenance is needed. This ML lifecycle diagram was introduced in our last lecture. Today, we'll discuss the tooling and approaches we can use for data collection, experimentation and evaluation, model deployment, model serving and inferencing, and ongoing model monitoring and maintenance. Data collection, ingestion, and ETL workloads are central for ML production systems. That said, these tools will often live externally to the services that train models and provide inferencing endpoints. It's a key separation of concerns. Data pipelines will run on separate schedules and have very different dependencies than the rest of our ML system. These kinds of data ingestion tools are generally supported by data engineers, not data scientists or ML engineers. They require different expertise in data management and data optimization. Some of the most widely used open source tools we can use for managing our data ingestion include Apache Airflow, Argo Workflows, and dbt. And for streaming data, we can use Apache Spark. Your tool selection will depend on your data engineering team's preferences, cost considerations, open source availability, and the level of community support available. Cloud providers often offer their own data pipeline tooling. AWS has Glue, for example. These tools are designed to let us centralize important data without needing to consider downstream requirements as part of our production systems. For example, our applications may be running and writing log files to an Elasticsearch logging system. We can then use data ingestion tools to transform those log files and pull what's required out of them into a data warehouse. That process of extracting, transforming, and loading data from a source to another data store is called ETL. There's a parallel practice known as ELT, which is where we extract, load the data into another store, and then transform it, but it's less widely used. If we need to perform operations on our data, the ETL approach is a more popular pattern as it lets us condense two steps, load and transform, into one. Apache Airflow is one of the most commonly used open source tools for scheduling ETL operations and orchestrating our data pipelines. Airflow does this through the use of a directed acyclic graph, or DAG. Data tasks are represented as nodes in the DAG. This lets us set up many steps of data transformation tasks as part of the same pipeline. dbt is an open source tool that lets us create a data orchestration platform. We can write transformations as SQL select statements, and we can create pipelines using YAML and Python. Jobs in dbt are also represented in a directed acyclic graph. Once we've extracted and transformed data from our production databases, like a customer database or an application database, we need to load that transformed data into another data store. This data store needs to be optimized for easy data discovery and querying, and should be able to handle heterogeneous data and multi domain data. For this use case, data warehouses are excellent choices. Although they aren't open source, data warehouses like Snowflake, BigQuery, Amazon Redshift, and Databricks are all excellent options. These services fall under the database as a service PaaS category, meaning us as developers don't worry about creating or managing the underlying infrastructure or software that make these data warehouses work. We only worry about getting our data into the data stores and managing accounts, connections, and schemas. S3 is another viable data store for ETL. And as we saw in our serverless lecture, S3 can act as an intermediary step in an extract, load, transform approach to data pipeline operations. Data cataloging and management are sometimes seen as low priority tasks, but they can make or break downstream services that rely on high quality data, like our ML services. Data cataloging lets us provide meaningful descriptions and definitions for the data that ends up in our warehouses. Imagine searching through a large scale data warehouse that ingests data from hundreds of production databases without having any hints or clues as to the provenance of that data or what the fields in the tables mean. Data cataloging lets us document our data in ways that can save headache and avoid wasting cycles training on data that may not actually represent what we think it does. Some open source data cataloging tools include CCAN, Magda, Metacat, and Open Metadata. Open Metadata is an open source tool that helps us manage and catalog our data in production warehouses. It was built by Colate and the founders of Apache Hadoop, Apache Atlas, and Uber Databook, and has over 10,000 open source members and 350 code contributors who support 90 data connectors. Open Metadata provides a unified metadata graph that centralizes metadata for all of your assets. It's designed to make it easy to collect all of your metadata and provide unified experience that brings data teams together in a shared responsibility and contribution. Having well-maintained metadata helps our data users with discoverability or finding key data assets to do their work. Lineage tracking helps us understand overall data flow. We often want to include lineage tracking at the column level, given that we ingest data from multiple sources into one table. A successful data strategy in an MLOps ecosystem will ensure that queries and transformations are repeatable, that ETL pipelines are managed in source control, that data is managed collaboratively through a team of data scientists and data engineers. Data cataloging is well worth the effort for the success of long term initiatives. Now let's talk about experimentation and evaluation. In this stage, we need to persist experimental results, showing which hyperparameters worked well, what training data was used, and record specific details about our model architecture. We also need to be able to collaborate effectively with other engineers throughout this process. A critical component here is the model registry. Think of a model registry as being like a container registry, but it's tailored specifically for storing trained model artifacts. This registry can store the actual model binary, as well as hashes of the trained dataset, and any other resources required to serve your model. MLflow is an open source tool developed by Databricks that lets us track our experimental results, as well as save our model artifacts in a model registry in one unified platform. MLflow lets us use model versioning, record metrics and parameters, and compare experimental results. Once we've completed our experiments and determined the model architecture, features, data, and hyperparameters we will use, we then transition to productionizing our work. This is one area where our tooling can make a huge difference. Our tooling can let us go from experiment management straight to deploying our model into production. By using a model registry, we can select the model we want to use in production by referencing the model version, pull that model's artifacts, including the model binary itself, and deploy that model into a production system. MLflow is extremely helpful in moving our models from development into production. By using the MLflow artifact store, which is the MLflow model registry, we can persist our model binary directly into a location that can be queried and pulled by other services. MLflow also includes sample code that lets us validate our model's inputs before we deploy it. The model schema is automatically logged, and dependencies and environments are persisted for us and made available in the UI so that we don't have to guess how to recreate our experimental environment in other places. When deploying into production, we can reuse some of the techniques we've already learned. These include using CI/CD pipelines to ingest the production-ready model into a container image, conduct verification tests, and use containerization and scaling techniques we've covered earlier in this class. Let's take a look at CI/CD for MLOps, specifically for deploying a model into production. Recall that CI/CD is automation for continuously integrating and continuously delivering our services. In an MLOps context, CI/CD includes building the model, running basic checks, and generating explainability reports. We can use CI/CD to deploy our model to test environments where we can validate the model's performance using metrics like accuracy, precision, recall, F1, or other task-specific metrics. We can also determine how well the model performs from a computational resource perspective. This can help us determine if we have any special considerations for resource allocation in production. Once we've tested and evaluated our model's performance in a pre-production environment, we can then deploy it into our live production environment. One way to automate CI/CD tasks for our MLOps pipelines is to use GitHub Actions. We can use GitHub Actions in creative ways to build pipelines for almost every stage of our end-to-end MLOps workflows, including data preprocessing, model training and evaluation, deployment, monitoring and alerts, and packaging and deploying our model into production environments. We've discussed the importance of persisting model artifacts, but let's explore what they are in more depth with a little more context. Our model artifacts include the code that we use to pre-process data and generate our model. This includes the model code itself, as well as pre-processing code, which can be deployed as a separate microservice if needed for reuse across multiple models. Artifacts are also the hyperparameters we chose for our model and any other model configuration we've applied, along with training parameters such as max depth, decision criteria, epochs, and input dimensions. Once the model is trained, an artifact is also that trained model in runnable form, which could be pickle files, joblib files, or other serialized formats, along with the environment needed to run the model, like the libraries used to run the model, environment variables, and so on. The data we used for training and validating our model are also artifacts. We need to store both training and validation data, using hashing for data record persistence, as well as the queries used or CSV files that were part of our data pipeline. Next, we want to make sure that we're using a code deployment strategy that makes sense for our model and our environment. When deploying our model, we want to first make sure that we're avoiding downtime, especially when the model is used for real time scoring. Two kinds of deployment strategies we may want to use when releasing a new version of our model include blue green deployments and canary releases. Blue green deployments are when we have two identical production environments, one running the current stable version of our model and one running the new version. We can then switch traffic over from the old version to the new version once we're confident that the new version is working correctly. A canary release is when we keep the stable version of our model running, but we redirect a small percentage of traffic to the new version. We can then monitor how the new version is performing and decide whether to fully roll it out or roll back to the stable version. This approach is particularly useful for A B testing approaches where you want to compare model performance. Our overall considerations for model deployment include making sure that any artifacts, including data artifacts, that were created during the training process are available for downstream services and tasks. We need to make sure that we persist a record of our training data and verify that the training data was what we said it was through attestation techniques. We need to make sure that we are securely reading our trained model and securely writing our trained model. In some production environments, we may not be able to write our model to disk after training. We need to make sure that we understand our hardware requirements for production environments and whether or not we may need to disable container resource constraints. Lastly, when deploying ML models in production, there are so many audit tables to think about. We want to make sure that we're recording our model version, evaluation results, feature importances, a record of our training data that is attestation, as well as model attestation. Let's move on to model serving and inference. Inference is the process of using a trained AI or ML model to make predictions or decisions on new, unseen data. The key tasks in the inference stage are to understand the requirements of your particular inference strategy, whether you're conducting batch inference, online inference, or one off inference. We need to also ensure that the features and transformation processes we used during training are available for our inference service. We need to expose an API endpoint for any calling service that's going to require a decision or other output from our model, and then we need to make sure that our inference service can scale in response to demand. Generally, there are two kinds of inference. Batch scoring services are typically scheduled jobs that run daily or weekly, processing large amounts of data in batches when real time responses aren't required. Real time or online scoring is where a small number of records are scored according to system or state activity. You'll see examples of this in ad display decisions, user session scoring, and fraud detection systems, where you need instant responses to make critical decisions. The infrastructure that we choose to run our inferencing service on will depend on the type of inference you're conducting and the overall volume of requests to your inference service. Let's take another look at MLflow. So far, we've looked at the features of MLflow tracking server. There's another important component to MLflow called MLflow serve. We can serve our ML models using the MLflow serve functionality. MLflow provides multiple deployment targets, so we can serve our model locally using a Flask web server API endpoint, or we can serve our model in a production environment of our choosing. Another popular and open source tool that we can use for serving and inferencing is the Kubeflow ecosystem. Kubeflow is a CNCF backed open source ecosystem of Kubernetes based components that assist us in automating and scaling each stage of the ML lifecycle. Kserve is one of the components in Kubeflow that specifically lets us serve our model via serverless architecture. When considering how to serve our inferencing endpoints, there are key things to remember. First, streaming data, batch data, and one off inference will all have different requirements, and LLM inferencing's requirements are distinct from traditional ML. Our inference service needs to be able to access the same data preprocessing and cleaning functions as the training service. Endpoint availability is often the top concern with our inference service because it's the part of our ML system that interacts with the outside world. Because the inference service is exposed to calling services, we also need to think carefully about latency, and we need to consider bandwidth for any data transfer and requirements for our inference service to be able to respond. Lastly, it's very important to record our model's decisions to an audit table. Now let's dive into monitoring and maintenance. This requires understanding both model performance and system performance, as they're both essential for keeping your ML systems running smoothly. The inputs for our monitoring stage include model logs, ground truth data, if applicable, to monitor performance, and application level data. These combined help us determine if we are seeing any drift. Drift is the performance degradation of an ML model over time, which can be caused by changes in real world data and relationships that the model was trained on. There are two kinds of drift: data drift, where the input data's statistical properties change, and concept drift, where the relationship between the input variables and the target variables change. Ensuring that we monitor both of these kinds of drift is important for the ongoing efficacy of our ML initiatives. There are two kinds of data that we need to monitor in our ML system. The first is resource monitoring, which includes tracking CPU, memory, disk, and network usage. This also involves implementing health checks and heartbeats on your serving nodes to ensure everything is running smoothly. The second kind of metric we need to monitor is our ML model's performance metrics. For supervised learning, you'll track accuracy, precision, and recall. For unsupervised learning, you might track silhouette scores for clustering algorithms. These metrics help you detect when models become stale and need to be retrained. You'll also need to manage model metadata, which includes model version information, decision time inputs and outputs, system actions taken, such as block or allow decisions, and storage of model evaluation metrics for historical analysis. There are many excellent options that let us visualize the logs and metrics that we collect from our resources and ML systems. For data visualization, you can use Looker, Tableau, Power BI, or create custom dashboards in Python or JavaScript. For observability and alerting, Prometheus and Grafana are popular choices that integrate well with most ML infrastructure. Now let's look at a cloud-agnostic ML lifecycle architecture diagram. This architecture flows from left to right in a logical sequence. It starts with data collection, pre-processing, and feature engineering. Next, you have offline and online feature stores that reduce duplication across teams. This leads to training, tuning, and evaluation, followed by model deployment. From there, you move to batch or real-time inferencing, then application integration, and finally, monitoring with an alarm manager. Feature stores are a way of persisting engineered features. They can reduce duplication and the need to rerun feature engineering code across teams and projects. The online feature store provides low latency retrieval for real time inference and is optimized for serving. The offline feature store maintains feature value history and is suited for training and batch scoring. The model registry is a repository for ML model artifacts. It stores trained models and metadata, enables model lineage tracking, and acts as a version control system for your models. The architecture also includes several important feedback loops. The performance feedback loop informs an iterative data preparation phase based on model performance during the model development phase. The model drift feedback loop informs data preparation based on production deployment evaluation and determines feature effectiveness in production. The alarm manager receives alerts from your monitoring system, publishes notifications to target applications, and triggers retraining pipelines when needed. The scheduler initiates model retraining at business defined intervals and can trigger retraining based on performance thresholds. Finally, the lineage tracker enables reproducible machine learning, which is critical for academia, industry, and research. It recreates your ML environment at specific points in time and is essential for defending model decisions in legal contexts. Let's explore lineage tracking in more depth. Lineage tracking is the collecting of references to traceable model and infrastructure resource changes. Put simply, lineage tracking lets us understand what in our system has changed, whether it's infrastructure availability, model versioning, or data. Infrastructure lineage involves implementing infrastructure as code, or IAC, for eliminating configuration drift, and managing cloud resource provisioning and management. This ensures you can recreate the exact infrastructure environment that was used for any model deployment. Data lineage requires archiving database snapshots, storing data schemas and metadata in version control, and maintaining feature lists and previous versions. This allows you to understand exactly what data was used to train any given model version. Code-based lineage involves committing code changes to version control, tracking implementation code changes, and storing model algorithm code versions. This ensures you can always trace back to the exact code that produced a particular model. We need to track the lineage of our model's features as well. A list of all the features we use during model training needs to be available in a feature store or in a model registry. This helps us track any changes to our features down to the minute that we either started observing changes in our underlying data or when we introduced or changed features. Our model algorithm code should be tracked in version control so that any changes to the algorithm code at any point in time can be revisited. Lastly, we should maintain oversight over our model container image. We should track our container images in image repositories. Now let's look at some concrete cloud platform examples to see how these MLOps concepts are implemented in practice. Starting with Google Cloud ML architecture, you have several data sources available, including BigQuery, Cloud SQL, Vertex AI Feature Store, and Cloud Spanner. The pipeline follows a structured flow that begins with data extraction and validation using TensorFlow data validation. Next, you perform transformations using TFX transform, which then flows into cloud storage. From there, you move to model training and tuning using Vertex AI training. The fourth step involves model evaluation using TFX model analysis to ensure your model meets your performance requirements. Then you have model storage using Vertex AI Model Registry for version control and artifact management. Finally, you implement serving using TensorFlow serving on Vertex AI to make your model available for inference. Moving to SageMaker architecture, this is AWS's end-to-end ML lifecycle management tool that includes model versioning and metadata tracking capabilities. The key components include Amazon Elastic File System for scalable storage, VPC with private subnets for security and network isolation, S3 for training data storage, CloudWatch logs for monitoring and debugging, and the SageMaker API, runtime, and feature store for the core ML functionality. You also have SageMaker Studio domain, which provides integrated development environment for your ML workflows. The full process flow starts with your on-premises code repository, then moves through AWS CodeStar, Code Pipeline, and Code Commit for continuous integration and deployment. Next, you have your model and container registry for artifact storage. This is followed by an approval workflow to ensure quality control. You then deploy to a test account using CloudFormation infrastructure as code, and finally to your production account using SageMaker endpoints and API gateway for serving your models to end users. Let me wrap up by sharing some valuable resources for further learning that will help you deepen your understanding of ML ops and stay current with the rapidly evolving field. I recommend visiting ai-infrastructure.org. This resource provides an excellent tooling overview that covers end-to-end machine learning lifecycle tools, functionality mapping, and project comparisons. Another essential resource is the AWS Well-Architected Framework. You should review the Well-Architected Framework for your machine learning systems to ensure that each lifecycle stage in your ML system has these 5 critical characteristics. These include high availability to ensure your systems remain accessible, security to protect your data and models, reliability to ensure consistent performance, performance optimization to maximize efficiency, and cost optimization to manage your resources effectively. This framework provides detailed guidance on implementing these principles throughout your ML infrastructure. Thanks so much for watching, and we'll see you next time.